Section: Introduction. In this section, we discuss the advancements made with large language models, LLMs, and the role of the self-attention mechanism in their success. This mechanism allows us to evaluate the significance of different words in a sentence, capturing intricate relationships in the data. A key component of this process is the Softmax operation, which, when omitted or replaced, often leads to a drop in model performance. However, we identify two main issues with the Softmax self-attention. First, it can be numerically unstable, especially as we scale models to trillions of parameters. Second, as the length of tokens increases during inference, the attention scores become smoother and lose distinct peaks, making it harder for the model to connect relevant tokens and affecting its ability to handle longer sequences. To tackle these challenges, we propose a Softmax free attention mechanism that enhances numerical stability and performance with longer token lengths. We break down the Softmax operation into two parts: a nonlinear transformation using the exponential function and the L1 norm, which is crucial for maintaining performance. Our experiments show that while non-negativity of attention scores isn't essential, the normalization process is vital. We then replace the nonlinear transformation with various activation functions, creating attention variants that perform comparably to the original Softmax-based model. Additionally, we introduce a length-scaled Softplus attention (LSSA) mechanism, which incorporates a dynamic length scale factor based on invariance entropy. Our results indicate that LSSA outperforms standard attention mechanisms for both training and longer sequences. To ensure distinct peaks in attention scores for long token lengths, we present a re-weighting approach that helps the model focus on relevant tokens while filtering out noise. By applying a power transformation to the attention scores and the L1 norm, we amplify stronger attention weights and diminish weaker ones. Our findings demonstrate that this re-weighting can be integrated with various attention types, leading to improved performance. When combined with our LSSA, this re-weighted model shows promise in managing longer sequences, maintaining stable validation loss even at significantly increased token lengths while ensuring numerical stability. In summary, we make several key contributions. We decompose the Softmax operation, highlight the importance of normalization, develop competitive attention variants, introduce the LSSA mechanism, and propose a re-weighting approach that enhances the model's focus on relevant tokens. Section Summary. In this section, we explore the limitations of the Softmax operation in self-attention mechanisms, particularly its numerical instability and performance issues with longer token sequences. We propose a Softmax free attention mechanism, length-scaled Softplus attention, LSSA, which enhances performance by incorporating a dynamic length scale factor and a re-weighting approach to improve focus on relevant tokens, demonstrating superior results compared to traditional methods. Section: Length-scaled Softplus attention. In this section, we introduce length-scaled Softplus attention, LSSA, a new type of attention mechanism aimed at improving the scalability and performance of large language models, LLMs. LSSA builds on existing attention methods by adding a scaling factor that considers both the length of the sequence and the model's dimensionality. This addresses the challenges traditional attention faces when dealing with long sequences during inference. We use the Softplus activation function to add non-linearity while ensuring smooth gradients for stable training. Through our experiments, we tested various popular activation functions and found that Softplus outperformed the traditional exponential function, which supports its use in LSSA. Unlike scaled dot product attention, which uses a straightforward approach, cosine similarity attention applies the L2 norm to each row of the query and key matrices. This method tends to produce more balanced attention weights, which can improve performance across different tasks. However, in high-dimensional spaces, randomly chosen vectors often become orthogonal, leading to a vanishing gradient problem. Therefore, we need a scaling factor for cosine similarity attention that relates to the dimensionality. Previous research showed that changing the traditional scaling factor to a logarithmic function improves the ability of transformers to handle longer sequences. We extend this idea by adjusting the scaling factor dynamically based on the token length in different rows of attention scores. Specifically, we set the scaling factor to the product of the logarithm of the dimensionality and the logarithm of a matrix that represents the number of tokens involved in attention for each row. This ensures that our attention mechanism remains effective across varying sequence lengths and model sizes. We also discuss the attention reweighting mechanism. While scaled dot-product attention has been successful, it activates all input tokens, which can be counterproductive. Tokens at the beginning of the sequence are often less relevant, so they should have minimal influence on attention scores. Our experiments with ReLU-based attention showed a slight performance drop, likely due to the concentration of positive values around the diagonal of the attention scores. This sparsity limits the model's ability to capture important relationships across the sequence. To address this, we propose transforming all attention scores to the positive domain using functions like Softplus before applying normalization. This allows us to use the L1 norm, which is simple to compute and maintains the integrity of the attention distribution. We can view the Softmax operation in traditional attention and Softplus with L1 norm in LSSA as forms of normalization layers, followed by a reweighting mechanism. We define a matrix where every element equals 1, ensuring that the mean effective value of the attention scores remains constant. The ReLU function masks tokens with low attention scores, and raising the output to a power enhances the distinction among the remaining tokens. As the sequence length increases, attention scores can become smoother, making it harder for the model to connect relevant tokens. The power operation helps maintain sharp peaks in attention scores, ensuring the model can focus on the most relevant tokens. We will refer to the combination of the reweighting mechanism and LSSA as LSSAR for the remainder of this paper. Section Summary. In this section, we introduce length-scaled Softplus attention, LSSA, a new attention mechanism that improves the scalability and performance of large language models by incorporating a dynamic scaling factor based on sequence length and model dimensionality, while utilizing the Softplus activation function for better training stability. We also propose a reweighting mechanism to enhance attention score distribution, ensuring that the model effectively focuses on relevant tokens, particularly in longer sequences, which we refer to as LSSAR. Section: Experiments. In this section, we conducted experiments using 8 NVIDIA A180GB GPUs and the GPT-2 small architecture, which has 124 million parameters. We replaced the original absolute position embeddings with rotary position embeddings, ROPE, and applied NTK scaling to manage longer token lengths during inference. Our models were trained on the FINEWEB10B dataset, which contains 10.2 billion training tokens, over 18,865 training steps, and included 0.1 billion validation tokens. We explored the Softmax operation, which can be broken down into a nonlinear transformation using the exponential function followed by the L1 norm. We trained the GPT-2 model from scratch with and without these components to assess their significance. Our findings showed that using Softmax did not significantly impact performance compared to not using it, likely due to the masking operation in attention that enhances the model's nonlinear capabilities. In tasks without causal masking, performance dropped noticeably. We found that incorporating a nonlinearity improved performance, and the L1 norm also played a role in enhancing results by normalizing the attention score matrix, ensuring balanced contributions from each feature and stabilizing training. We also modified the standard attention mechanism by testing various activation functions, including ReLU, ReLU squared, ReLU6, JELU, sigmoid, Softplus, and MISH. Our results indicated that all activation functions, except Softplus, led to higher validation loss compared to the standard exponential function. This was due to the positive values in the attention scores being concentrated around the diagonal, causing other positions to remain negative and limiting neuron activation. Softplus, with its slower growth rate, focused more on distant tokens, resulting in lower validation loss. Next, we compared our proposed LSSA and LSSAR with leading Softmax free attention methods using the same GPT-2 model. We evaluated two variants of sigmoid attention, modifying a hyperparameter and applying the L1 norm. Our experiments showed that at a sequence length of 1K, all attention variants performed similarly, with slight differences in validation loss. However, as sequence length increased, the standard Softmax attention's performance declined, while sigmoid attention faced significant drops at longer sequences. The modified sigmoid showed some improvement, indicating that our proposed hyperparameter was more effective. We also tested the re-weighting mechanism on attention scores from Softmax, sigmoid, and LSSA. The re-weighting improved performance across all tested mechanisms, with different values being more effective for varying sequence lengths. Notably, LSSAR demonstrated remarkable stability, maintaining consistent validation loss even at 8K tokens, suggesting that our re-weighting mechanism effectively managed longer sequences by better distributing attention. Section Summary. In this section, we conducted experiments using 8 NVIDIA A100 GPUs and the GPT-2 small architecture, replacing absolute position embeddings with rotary position embeddings and applying NTK scaling for longer token lengths. We explored the impact of Softmax and various activation functions on model performance, finding that while Softmax is not critical, the L_1 norm and certain nonlinearities enhance performance, particularly in managing longer sequences, with our proposed LSSAR demonstrating exceptional stability. Section: Ablation Study for Re-weighting Mechanism. In this section, we explore the re-weighting mechanism we proposed by evaluating it with LSSA and Softmax attention across different values of the parameter page. Our findings, shown in the accompanying figure, reveal that LSSA and Softmax attention respond differently to changes in page at lower values of P. Softmax attention performs similarly to LSSA, but as P increases, particularly at P equal to 15, Softmax attention experiences significant gradient explosion issues. This instability is evident in a sharp rise in validation loss across all sequence lengths, making the model nearly unusable at higher P values. Conversely, we observe that increasing P generally enhances LSSA's performance across various sequence lengths, with the best results around P equal to 15. The validation loss remains stable as sequence length increases, highlighting LSSA's strong scalability. This stability may stem from the nature of transformers, which can be seen as smooth cubic splines, where the Softplus activation function is more natural and maintains fidelity with these representations. Additionally, since the derivative of the Softplus function is the sigmoid function, which has a maximum value of 1, LSSA is less prone to gradient explosion issues. To further assess LSSA's stability at large P values, we conducted tests with P equal to 50 and 100. We found that LSSA remains stable and avoids gradient explosion even at these extreme values, although we do see a gradual increase in validation loss. This increase occurs because larger P values create a sharper attention distribution, causing the model to focus mainly on the highest value and potentially miss other important contextual information. This indicates that LSSA can handle large P values effectively without numerical instability, outperforming Softmax attention in this regard. In our discussion, we note that while LSSAR was tested on a smaller model, GPT-2 124M, with a maximum token length of 16K due to limited computing resources, we can infer that the validation loss for LSSAR would remain stable for longer token lengths. We also consider that extreme P values can be viewed as increasing the depth of the GPT-2 to 124 meters model, suggesting that LSSAR would likely be stable for larger models with billions of parameters. Implementing LSSA and LSSAR using PyTorch's built-in functions can be resource-intensive, so we recommend developing a highly optimized tensor program, like FLASHATTENTION3, specifically for these components. However, this requires a solid understanding of hardware and CUDA programming, which can be quite challenging. Alternatively, we might use Mirage, a tool that automatically finds suitable CUDA kernels and generates optimized tensor programs. We also suggest using the T6 model with LSSAR in practical applications. T6 utilizes tensor decompositions to compactly represent queries, keys, and values, significantly reducing memory usage while improving performance compared to standard transformers. By replacing Softmax attention with LSSAR in T6, we expect the model to efficiently handle much longer sequences under fixed resource constraints and demonstrate better length extrapolation capabilities. In related work, we note that previous studies have explored Softmax-free attention by replacing the Softmax function with ReLU, squared ReLU, and sigmoid activations, as well as examining purely linear attention. However, none of these alternatives surpass the original Softmax attention. In contrast, our proposed LSSA shows improved numerical stability and better performance across various token lengths. Regarding attention reweighting, the nonlinear reweighting mechanism introduced by Softmax attention, which involves L1 normalization, has been shown to concentrate attention weights and stabilize training. Our empirical findings further highlight its importance in maintaining the performance of large language models, LLMs. We also introduce a new perspective, a nonlinear positivity transformation followed by L1 normalization. Inspired by the classic normalization ReLU structure, our reweighting mechanism masks less relevant tokens while amplifying the relevant ones, enhancing the length extrapolation ability of the underlying models. This contributes to a deeper understanding of the attention mechanism within transformers. Finally, we emphasize the critical role of positional embeddings in transformer architectures for improving length extrapolation. Among these, rope stands out as a foundational element in many modern LLMs, including GPT-4, Llama 3, Qwen 2, and DeepSeek v3. We modified the underlying model, GPT-2 to 124 meters, used in our experiments to incorporate rope, and our LSSAR method significantly enhances its length extrapolation capabilities. This suggests that a well-designed attention mechanism like LSSAR is vital for rope-based LLMs to improve their length extrapolation, indicating that LSSAR could serve as a general strategy to enhance the length extrapolation abilities of most contemporary LLMs.